Hi, this is my tracker, and this is my Make Your Own Lab 5 energy loss from falling object. The purpose of this lab is to examine the motion of a paper ball falling to evaluate how much energy is lost in the system. The models we'll be using is free body diagrams, glow script, and tracker. The physics principles is Newton's second law, F equals ma, momentum update principle, and the energy principle. The preview results is that the predicted model will have the potential energy reach zero faster than the actual model, and there will be a significant amount of energy loss in the actual system compared to the ideal system. So this is a video of the falling paper ball. Okay. And then, so the system and assumptions is that the surroundings is the air, the system is the paper ball, and Earth, assuming that those are the only forces acting on the mass. We're assuming there's no air resistance and loss of energy for like the ideal system, and we're assuming the constant net force is acting on the mass for the model, and due to Newton's second law, F equals F net is going to equal Fg for the ideal model. But as you can see here, I have on the right, I have a free body diagram for the real system, which has a small amount of rotational kinetic energy and force of drag. But we're assuming that force of gravity is only acting on the object for the predicted ideal system. The initial conditions is that the initial velocity is 0, the mass is 0.07 kilograms, and the force of gravity is 0.687 newtons. The floor is the origin, and at rest the mass is at position 1.05 meters. So I use Newton's second law, the F net equals force of gravity, and then the force of gravity is equal to mg. I use position update and velocity update, and for total energy I use the potential energy of gravity and the translational kinetic energy. And to get work external, I took the initial potential energy of the system, which would give me the total energy of the system, and subtracted that by the kinetic energy and potential energy at the time to get the graph for the change in work external. Over here, this is the actual position. So I use tracker to analyze the video to get all the points and where it falls, and I put that into my code, which I'm about to get to in a second, to find the amount of potential energy it had over time, as well as the kinetic energy and the energy lost in the system. So for the predicted position, this is the code I use to get the energies and the position graphs. So I calculated the force of gravity, and then I calculated the velocity of the ball, and then the position to get the kinetic energy, and then the potential energy for my predicted model. And I just did the same thing with the actual model, except that I already had the positions. So this is my predicted position graph. I have the data to the right for predicted and actual. As you can see here, the total energy of the system stays constant because there was no energy lost in this ideal model. So the conclusion is that comparing the ideal and actual systems show that the amount of energy lost was approximately 0.4835 joules, which was used by subtracting the initial potential energy by the kinetic energy final, and then the total initial energy was, like I said, 0.72 joules, and then that means that there's 67.12% of the energy lost to outside forces. The lost energy graph closely follows the translational kinetic energy, so that shows that most of the energy loss was to drag. So possible errors could have been from plotting on tracker, as well as turbulence caused from the wind, creating like rotational kinetic energy. As you can see here on the x position versus time graph, it goes to the right. So what does it mean? Further, your model of the system is all the energy lost to air resistance. It's not, because the ball in the video slightly rotates, so there is some rotational kinetic energy, so not all the energy is lost to drag, but also some to rotational kinetic energy. And what if using the same system in surroundings, how would the results change if there was a heavy mass used? So there wouldn't really be a change in a direct change in how much energy is lost, because force drag is equal to dv squared, which d is a constant and there's no mass in the equation, and work done by the force drag would have been force times the times distance. So there's no direct relationship between force of drag, change in mass, and energy. Thank you.